Hello, we are discussing the third design technique, which is based on feasibility maps, which is in turn related to the spring lever model. And we already discussed how to construct a spring lever model for a given compliant mechanism and how we can construct the feasibility map for given user specifications. In the last lecture, we discussed how the selection process as well as redesigning process work. Today, we will consider two case studies to illustrate what we discussed in the last lecture regarding selection as well as redesign. So, let us look at the two case studies, and again the keywords here are the feasibility map technique and designing compliant mechanisms by selection and redesign. So, here is the case study 1, which is an example that we had used as a motivation in the first lecture that described this technique of using feasibility map, where we have a piezoelectric patch which has its own stiffness, which is what we called Ka, which is the actuator stiffness, and this piezoelectric patch can give some force, which is our input force, and it also has some stroke, which is the input displacement. And all three of these we have let the user specify a minimum value as well as a maximum value. There is a lower bound and upper bound. So, for example, this actuator can provide input force of 800 newtons. Since we want precisely that value, we put lower and upper bound to be the same, and input displacement 80 to 100 microns. So, the 10 power minus 6 meters. So, there is a range, there is an input lower bound and an input upper bound on the displacement, and K actuator that is fixed here. So, we just have specified the same number for lower bound upper bound. That is perfectly possible. When you have a fixed value in mind, you can specify lower and upper bound to be the same value. And then the output port, we have indicated how much force is there, that is 200 newtons precisely, that is what you have, you put the same number. And how much displacement you want? Let us say you want 300 microns, we specify lower bound to be 290 and 310, because you can live with 10 microns less or 10 microns more. If that is the case, when you have in mind you out to be let us say 300 microns, you can enter that to be anywhere from 290 microns to 310 microns, if that is what you can tolerate. If you cannot, we enter the same value for both of them. Okay. And then there is also external, K external, which in this case is specified to be 0, meaning that there is no output spring, there is only output load, there is no output spring. Sometimes there may be only output spring, but there is no output load. In this particular case, we have output load which is specified here, but there is no external spring. So, 0 0. Okay. Now, when we have specifications such as these, we want to know whether there can be a compliant mechanism that can give this, that can use this actuator, be within the restrictions that we have shown here and deliver the output as it is desired here, okay, whether such a mechanism is there or not. The first thing to do is to do a little bit of analysis, analyze those specifications. User can ask anything, first we have to see whether that makes sense or not. How do we check? Let us say we have Fn equal to 800 newtons and output displacement, let us say we take this 100 microns, 100 10 power minus 6. Okay. Usually these piezo actuators would have the force, if I call this indicate that on the force axis, and then this is displacement axis. Okay. If we have that, then it will go like this, it will be 800 over there and then become 0 over the stroke. So, the area under this input energy we have to divide by half. If we do that, it will become 400 into 100 10 power minus 6, the units are Newton meter, right, because you put this all in Newton and meter units. That means that what do we get here? 4 into 10 power minus 2 Newton meter, that is what we get here. And if you look at the output, so we have output, this is the input energy, this is input energy. That is what our actuator is able to deliver over the maximum displacement of 100 microns. So, now let us write the output here. So, F out is 200 newtons and let us say nominal is 300 microns, 300 microns, this is Newton meter, that will be, and it is not half because 200 newtons will be acting, we are assuming all the time throughout the range of motion. So, output moves by 300 microns, it would be working with this force 200 newtons all through this 300 microns. So, what I get will be 6 into 10 power minus 2 Newton meter. So, this is output work or energy, output work or output energy. Okay. Clearly, this is not going to work because output is more than the input. So, we have this output 6 was only 4 10 power minus 2. So, it is not going to work. So, immediately we can say that this specification of the user does not work. This is an obvious thing, you can do the energy calculation like this and then say that it is not going to work. Okay. But the point here is sometimes when the user specifies all these lower and upper bounds, what might look possible based on this simple energy calculation like this actually might not lead to a particular mechanism. So, that is where we bring in our selection map with the feasibility map as well as showing compliant mechanism within that feasibility map and then see if a mechanism in the database will work or not. Okay. So, now what we will do is to proceed with this example, let us decrease the force. Now, what was 200 newtons, we decreased it to 10 newtons, rest of it stays the same, 800 newtons of input force over 80 to 100 microns of input displacement. Output is only 10 newtons now and output displacement is again nominally 300 microns, but it can be plus or minus 10 microns. And then we have actuator stiffness 7.5 10 power 6 Newton per meter, no external spring force. Now, if you have these specifications, now we can see that what was 200 we made it 10, that is we reduced it by a factor of 20, that means that we have plenty of input energy. Now, 6 by 20 is what we have, there you have 4 in 10 power minus 2, 4 is there. So, we have plenty of input energy and part of that energy can be used to deform the compliant mechanism, that is input energy can be split into output energy and strain energy for deforming compliant mechanism that we are going to design. So, this technique is all about before designing we can make some inferences about what we are going to design. Okay. So, we can take this input energy which is 4, now this is only 10, okay, the factor of 20. So, it will become 6 by 20 and whatever 10 power minus 2 we had done earlier. So, it is a lot of left out energy, that is 4 minus 6 by 20 times 10 power minus 2 Newton meter, that is available to be used as strain energy. Okay. So, we analyzed it simply and realized that those specifications are not good. Now, we have something that makes sense, just simple accounting of input energy and output energy, but that is not enough for us to say that these specifications are actually possible with a real compliant mechanism. So, for that what we do is draw the feasibility map. So, whatever numbers that we had, we have put them all here, there is 800, if you zoom in we will be able to read, and then displacement we want output displacement, output load 10 newtons and in that input displacement, output displacement, spring constant, K external, all of them are indicated here. If we zoom in, we can find that all there. Okay. Now, we got this feasibility map. So, these all the thing that is bounded by this green curve, feasibility map. We also have a number of mechanisms that are plotted in this KCI versus KCO plot. So, what we have here, if I zoom in a little bit, okay. So, here we have KCO and we have KCI and we have the feasibility map. Now, hopefully you can read the numbers that are entered here, okay. 80 microns to 100 microns of input displacement, 800 newtons of input force and all of that. So, we now have, we can see some of the mechanisms also there, and we can actually click this button and then say show mechanisms. In this case, we are saying show first 8 mechanisms. If we count, I think there is some overlap. There are 8 dots here. They are on the boundary. We have to see whether they are inside. If they are inside, they definitely satisfy the KCO and KCI values, but N value also has to be checked. Okay. So, if you look at, and we can also see that mechanism is shown and what material it is, and there are more details as was there in the previous slide. We are looking at only a close up view of a part of the feasibility map window. Okay. So, now the selected mechanism you can say. So, as I said, we have 8 mechanisms we wanted to show. We can show more, as many as you want to see, but these are the one that is going to be closest to feasibility map or inside the feasibility map. Inside the feasibility map, first they will be there, and then the things that are closer. If none of them inside feasibility map, it will show the 8 mechanisms whose points on the map are closest to the edge of the boundary of the feasibility map. We select the mechanism 8th here by clicking or by choosing here, then the mechanism will show up there, and that will have a lot of information about that, what material it is, how does it look, and even do an animation. So, you can see how it is going to behave. This particular one is going to be fixed here and here. The user has to know all this, because in this technique, as we had noted earlier, we are not going to let the user specify where it should be fixed. In fact, our argument is that many times user might not have any preference as to where to fix. User is interested in input output ports, and there may be a preference for where it should be fixed after the main functionality is served. Now, when you show a number of mechanisms, user can say, oh, this is what I like, this I do not like, or maybe this is too difficult to manufacture and things like that. Based on that, one can choose a mechanism of interest. Okay. We can see the animation and 3D model and all of that, know what material, and as we will see, what manufacturing processes can be used to make that compliant mechanism is also there in it. Okay. In this particular case, when we zoom in and look at a point that is somewhere there, which is slightly inside, just inside, but very close to the boundary, but there is a problem. N value, if we can read, this is N minimum and maximum, that is what we had said. Any point inside the feasibility map will have a corresponding range of values for N. So, this one will have a range of values for N. There will be a N min and there will be an N max. Okay. In this particular case, min is 8.74 and max is 9.76. There are 2 decimal places, it does not matter, but N of the mechanism that we have chosen happens to be minus 9.86. Even if you ignore the sign, which you should not, because mechanism has a sign for N, positive or negative. If it is negative, it is an inverter, that is input and outputs are opposite directions. If it is N is positive, they are more in the same direction. Here 9.86 is clearly outside this range. So, this mechanism is not suitable for us. So, we can find that there is nothing else inside. Okay. Then what do you do? That is when we try to redesign it. What we do is we try to change a number of things that we had discussed earlier. We can change the in plane width, thickness, material, size in x, size in y, all of those we can change as we wish, and then see if we satisfy KCI KCO, that is where inside the feasibility map, and at that point whether n lies within the range corresponding to that point, because every point in the feasibility map, KCI KCO, stiffness map or feasibility map will also have a n, because what we are seeing is only a projection of a 3 dimensional volume containing the feasible values of KCI KCO and n. So, n will be there, that n has to correspond to the or has to agree with the n of the compliant mechanism. So, we try to change and we put some limits of these, we can change thickness, material and all of that, and try to see. Now, as you can see, the size is taken care of, because size in x and y we can put some values, whatever units that the user wants to be consistently using. Manufacturing aspects, because we have indicated the material and thickness and in plane width, all of those correspond to the manufacturing processes, and strength as well, because anytime you click this button maximum stress in the gradual interface, the stress value will be displayed here. You can compare the strength of material correspond to that material that you have chosen, we can see whether it is satisfied or not. So, everything can be accounted for in this particular method. So, now with those things we can go to the redesign. So, redesign here means that the point that was there was not satisfied. So, we construct some parameter curves. Parameters are here, we can change material. Thickness plus means that you can increase thickness and then see what happens to KCI KCO, and if you click on it you would also know what n value will be there, and then thickness minus means that you are decreasing the thickness, and then in plane width increasing or decreasing, size in x increasing or decreasing, size in y increasing or decreasing, or simultaneously you can increase size in x and y, simultaneously decrease the size in x and y. All of those things will be shown like curves that are shown here, and they are all in the KCI KCO map. So, x axis you have KCI, y axis you have KCO, and of course, anytime you want you click and you will find out what is the range of n is. Okay. So, until it is satisfied you keep on changing. When you do so, in the window it also shows for any mechanism that you have chosen in green which are possible processes. In this case laser micromachining and CNC milling are applicable, whatever people who stored the mechanism in the database know with what manufacturing processes that mechanism can be made. We indicate that in this particular case CNC one is milling is chosen, and there you can enter in millimeters. In this particular case the gap, minimum gap that can be done, minimum features that can be done, minimum thickness that process allows, maximum thickness also, because silicon in micromechanisms will not allow very thick structures. There is a max thickness also, just as there will be min always, and minimum size and maximum size depending on what process you are using. You can enter all those manufacturing process parameters and then try to change them. So, we started somewhere here, go somewhere and then comes back. So, you can basically use it like almost like a game, if you will. It is like a game where you start somewhere, it is not satisfied, move along one of those parameter curves and see if you enter the feasibility map. If you enter, check n value there, n will have a range. If it is inside the range, you are done. If it is not, change again from there, draw parameter curves and you can do that. So, in this case something like that is shown, you are started inside somewhere, went there and then draw the curves and come back. So, you are at some point. Okay. At that point, if everything is fine, meaning that n is within the range which it is. So, here you can see n min, if I write minimum value of n for that point, okay, is 8.96, maximum is 10.08, and N of the mechanism is 10.07, almost close to the maximum, but nevertheless it is in the range. So, we are done. So, we have a solution. We have a solution to the user specifications that are given, right. That is how we redesign. So, the redesign mechanism you cannot see unless you zoom in, that information is there. You got inside, look at the mechanism and what process is suitable for this, what are the manufacturing parameters and what is the maximum stress. All of those can be found out from the user interface by clicking a few buttons, software buttons, it is not real button. So, we have designed the mechanism. Redesign mechanism, you can look at it. Now, the material has changed to aluminum. Originally it was polypropylene, but we changed the material in the parametric curves and got that mechanism looks like this. You know where is input and where is output, and you can proceed with it. Okay. That is how this method works. Now, let us take something going from meso scale like a piezo actuator or a macro scale. Let us go to the micro domain, where we look at a micro machined accelerometer. Previous case study was a piezo actuator, something output has to move. It is more like an actuator, where compliant mechanism is acting like a transmission. It takes the actuator and transforms the input output features suited to a particular application. That is what a transmission does, that is what we got. Now, let us look at another study, case study, a second case study, where we look at a sensor. If you have a sensor, how do you make it more sensitive through mechanical amplification is the purpose of this sensor. It is an accelerometer which measures the acceleration of a body on which the sensor is mounted. So, it is shown here. Usually accelerometer will have a what is called a proof mass. Okay, there is a mass. When there is acceleration, it is going to deform. It is going to deform, and there are these beams which we call a suspension. This is the beam suspension. It will move and you can measure the displacement electrostatically, but what we say here is that instead of doing that electrostatically sensing over here the movement of the mass in that direction, we amplify it here. What was here has now moved to here. So, it is a lot of displacement from here to here, where input has not moved much at all. When output moves a lot, here is where you can put the comb fingers and measure the change in capacitance. So, your sensor becomes that much more sensitive. So, you are trying to look for what we call a DACM. So, displacement amplifying compliant mechanism, that is DACA, displacement amplifying compliant mechanism, as it is written here, is what we want to design. And for this also we can write first specifications. So, before that, let us also remember or remind ourselves about the spring lever model, where we have again KCI, N and KCO. As we will see in the next lecture, we can also talk about MCI and MCO, input side mass or inertia, output side mass or inertia. Right now today we are going to discuss only the static applications related to the accelerometer. So, what this slide shows is that just like a structure can be represented using a spring and a mass, a compliant mechanism can be represented, in this case DACM, displacement amplifying compliant mechanism, can be represented using the spring lever model, and the two equations U out and U in and net amplification, that is a particular definition, we will look at that later. Anyway, there is a analytical model for the spring lever model, and we are using that along with the concept of the feasibility map. So, in this particular case what is done is that if you take an accelerometer, in this case some researchers Abdolwand et al. 2007 had published an in plane capacitive accelerometer that basically looks like this. These are the beams, okay, this is the beam suspension. you can hardly see those, very small, and there is a big proof mass, okay, and that has some frequency which we will come to later because that is dynamic consideration, at least not static, and there is some thickness and so forth, and the proof mass has to be 38 milligram and 110 centicohm fingers, that relates to how much capacitance is there. Frequency, static displacement sensitivity is 6.5 micron per g, that is if there is an acceleration due to gravity of 1 g, then the proof mass should move by 6.5 microns, and the capacitance is 30 picofarad per g. That is how we get the specs. Now, for these specs we can calculate the equivalent input force and then set aside how much input displacement will be there, how much output force we want. Output force is not there here because just a sensor, it just moves and capacitance change is detected. There will be little bit of electrostatic force, but you do not worry about it. There is no output force, there is an output spring because that suspension will add a little bit of stiffness, and displacement, the more the merrier, because for given g, if it can move by let us say 1 micron, then you can resolve much smaller through capacitance, then you can actually get a fairly accurate value of whatever you are going to measure. Okay. So, in this particular case what we have done is we have extracted those in terms of the specifications. Fn is 190 micronewtons to 110 micronewtons, that is 1 g acceleration times the proof mass mg basically, and then input displacement is asked to be between 2 microns and 3 microns, and then F out is 3 micronewtons to 4 micronewtons, and then output displacement 7 microns to 11 microns, and there is Ka stiffness actuated to 70 Newton per meter, and 0.3 Newton per meter to 0.4 Newton per meter is the K external, that is stiffness that you have for the output side. With those things we can draw the feasibility map again. Feasibility map is very small, and if that is not satisfied, most often it may not be in terms of n also. Then you try to do this parametric curves and try to get what you want. So, here we have that feasibility map, n as the mechanism 6.04, n max 6.05, n min is 5.76, clearly n is within the range. Let me write that in case you cannot see there. N min is 5.76, whatever the units, in this case n has no units, and 6.05. N mechanism that satisfies, that inside the feasibility map is 6.04, again very close, but the method is finding something that is possible with n value, not just KCI, KCO. You have those, and here is the mechanism. Mechanism looks like this. It is fixed here, and it is fixed here, and here is where the input is, and here is where the output is. It is a DACM, displacement amplifying compliant mechanism. Okay, we can see if that is fine. Sometimes having an anchor inside like this may also cause problems, but there are ways to deal with it. User can choose, and in this particular case it is also showing that micro machining is the only possibility for making something like this, because the user would have put in such information into the software. And we modify that Abdul-Wand's accelerometer by replacing compliant mechanism in between the proof mass and the sensing mass. When you do that, we actually see that for the same footprint, that is 3.9 millimeters 5 millimeters, static displacement sensitivity of 10.51 micron per g unit acceleration to gravity, sensitivity improvement of 60% over Abdul-Wand's design. So, you can take the best accelerometer that is there and make it better by adding a DACM, displacement amplification compliant mechanism. We will be talking about that in another separate lecture later on in terms of detail, but the purpose here is to show that we are able to design an accelerometer, or rather a compliant mechanism or a DACM, displacement amplifying compliant mechanism for a given application. Here the application is an accelerometer. So, we can do later the analysis, frequency analysis and so forth, and later on when we discuss the dynamic equivalent of SL model, which we call spring mass lever model or SML model, then we can actually look at the frequencies that simulation shows and the frequency that that experiment would give. There is a difference, one has to figure that out. There can be another case study which we are not going to discuss in detail, but we will take it up later, where again another DACM, but here there is no output force, there is no output spring. It is simply a sensor that has a probe which you can see here, a little probe. A small force applied will amplify the displacement over there, that little red thing, and you want it to be large enough to be picked up by a digital microscope. So, digital microscope is here, and that can pick up the displacement, we can calculate the forces. With this we could do a resolution of 2 micronewtons per pixel, and with a range of about 1.4 millinewtons, or rather 1400 micronewtons force is what we can detect, that range, the resolution of 2 micronewton per pixel. In this particular case, since there is no output load or force, KCO does not matter. In fact, what we will see later on is, in this case feasibility map will be only 2 parameters. We can just say okay, here is KCI and here is N, because KCO does not matter when there is no output load or output spring. Here also there will be a feasibility map, and we can put all the mechanisms inside that. So, there could be some inside, some outside, no matter how it is we can detect that. If you say okay, this let us say this one, the N value matches, that is taken, N value does not match, you throw it away, N value does not match, you throw it away. So, you can keep on going like this until you get what you want. Sometimes you may have to change parameter curve, let us say from here it comes along 1 and that N value does not change, again you go along another curve and finally end up here. That is what we discussed in the last lecture. Through case studies we illustrated this, but you will also get a demo of the program where you can see how it is done both in MATLAB as well as in Java. There are 2 versions. As supplementary material you will have access to these programs. So, to recapture the main points, this is exactly what we had done in the previous lecture. We can investigate the feasibility of a mechanism before designing it, and after that we can select and redesign it. And what are important here is to note that there are these properties of compliant mechanisms which are spring lever model parameters is what we are looking at. So, the PhD thesis of Sudarshan Hegde is the basis for this method, that he had developed this method as part of his PhD thesis. So, that is available to you and you can read that, or 2 of the papers that Sudarshan has written, one in mechanism machine theory, another one general mechanical design, are also available for further reading on this topic. Thank you.